Good morning. Today we are going to binding energy part 2. Binding energy part 2, we're looking at nuclear reaction and Q value. In part 1, we learned that the total mass of the nucleons in the nucleus is greater than the mass of the nucleus. And this difference in mass, we call the mass defect or mass excess. Difference in mass between the total mass of nucleons in the nucleus and the nucleus. Or in mathematical symbol, this is the total mass of neutron. This is the total mass of proton. And this is the mass of the nucleus. Right? Delta M, just to show a small difference. Then we calculate our binding energy using Einstein's relation, delta mc squared, where delta m is in kilogram, c is the speed of light, 3.0 times 10 to the power 8 meter per second. Right? And the value binding energy E is in joule. So if the mass disappears, it appears as energy. Or if you are given in atomic mass unit, you want to gain the energy, we just use 931 mega electron volt. 1 atomic mass unit equals 931 mega electron volt. So we can write a equation, right? Nuclear equation. A is the mass of the incident particle, right? The particle you send to hit the other nucleus. Ma is the mass of the nucleus. Right? This is the target nucleus. Mb is the mass of the resultant nucleus. The nucleus formed as a result of the interaction. And Mb, mass of emitter particle, the particle that's ejected or emitted. And then there's energy release, Q. Right? And then we define the Q value, a measure of the release or absorbed energy released or absorbed in a reaction. So we define as total mass of reactant minus total mass of product. Right? A difference in mass we times C squared. Okay, or in the mathematical symbol, right, as total mass of reactant, total mass of product. Or if you are working, we can show mathematically if you are working with binding energy, then we start with binding energy of product minus binding energy of reactants. The other way around. Right? Hope in the first part, I've tried to show you the derivation, which you don't need to know. You just need to memorize how to use it, because the derivation can be quite complicated. Okay, just to satisfy your curiosity, right? Why we do it this way? Right? We look at one particular one. This is the product, right? Product. You have to find the total mass of neutron, total mass of proton, minus the mass of the nucleus. And then that difference multiplied by C squared. Right? You can see that minus there is here. Is here. Right? This one will disappear in our calculation. In the whole calculation there. And if you look at this one, the same thing. Right? This is the total mass of neutron in A. Right? A is a reactant, can be like nitrogen. Total mass of neutron, total mass of proton, minus the mass of the nucleus, A. So you can see that this minus and this minus become positive. That's why we get that. Okay, that's sufficient for you to know roughly why we do that. Right? If it's just like chemistry, if energy is given out, we call it exothermic reaction. That means the mass of reactant is greater than the total mass of the product. Or endothermic reaction. That means you require energy, you have to be absorbed before the reaction will take place. Then we get Q is negative. In this case, the total mass of product is greater than total mass of reactants. Okay, so we are going to, for the rest, we are going to look at some of nuclear reaction. Basically, we are going to look at 3 different types: fusion, generic, nuclear reaction, and then fission. Right? Not in that order, but roughly that's what we are going to cover, and then we are going to relate to the binding energy per nucleon graph. In nuclear reaction, the nucleus become rearranged. It's different. We start with a nucleus, like this one, uranium, and you send a neutron inside there. After the combination, it break up into two different daughter, krypton and barium, and then release of 3 neutrons. So the total mass, right? We look at mass, and total mass before the change must be equal to total mass, right? Total energy. Right? When we say total energy, we must also include the mass after the change. Right? Same. Total mass and total energy, including mass, before the change must be equal to total energy, including mass after the change. Right? Plutonium, alpha decay. Right? There's a release of energy. Where does energy go to? The energy goes to the kinetic energy of these two, uranium and alpha particle. We can calculate the kinetic energy of the product as total mass before, and then total mass after. That gives us a difference in mass defect times your C square. Calculate the energy release or required in a nuclei, in a nuclear reaction of any kind. We simply add all the masses before and all the masses after. Right? Subtract. Then we can convert to mega electron volt because it's convenient unit. Right? Let's look at nuclear collision when an alpha particle collides with nitrogen 14. Okay, that's the classic one. Okay. You should be able to write that equation. The oxygen is formed and a proton is emitted. Okay, let's look at mass. Conservation of mass energy. Mass different. Okay. First thing, this is the reactant. This is the product. So that's the mass in atomic mass unit. That's the product mass in atomic mass. You just add them up. Total mass 18.00567. Cannot round off, right? If there are 2, 4, 5 decimal place, you put 5 decimal place. Cannot round off. Same thing. You just add them up. You get 18.00696. Okay, you can see if you round off to 2 decimal place, these two will be the same because the change in mass is very small. So in this case, we can see after the reaction, the mass is greater than the initial mass. Right? What does it tell us? That the reaction cannot take place. That means you must supply energy to this alpha particle so that these two will have the same energy. Then the reaction can take place. Okay, we can subtract that. We see a negative sign. Show you is endothermic reaction. The reaction cannot take place. It means the two of them together will not interact. So the energy required, right, we just use that. Use that different there. We are not worried about negative sign. right? Times that 931, right? One atomic mass unit is 931 mega electron volt. Multiply that, get 1.20 mega electron volt. That means that is the minimum energy the alpha must have before the nuclear reaction will take place. Okay. For the reaction to occur, alpha particle must be projected with kinetic energy of 1.20 mega electron volt or more. Okay, we will see this. The problem is because the two nucleus are positively charged. So you want to force them together. You need to force the alpha particle to enter the nucleus of nitrogen. Okay, so you can see that both of them are positive charged. And the distance of closest approach, right, we can, under electric field, we have gone over that. We can calculate if it's where it's moving. You send it to the nucleus. I say this is nitrogen. This alpha. Then we have the loss in kinetic energy of the alpha particle equals to gain in potential energy. If you want to find the distance of closest approach. So that equation gives us a minimum kinetic energy. And the minimum energy to determine the distance of closest approach, or roughly the radius of the nucleus of the parent and nucleus of the alpha particle add together. Okay, we can use this formula. V potential of the nucleus and that charge there. Okay, fission. Right? This is origin nucleus. Fission occurs when the origin nucleus splits into two. It splits into two. Radioactivity, only one. And then emitter particle. The two we call daughters are roughly not equal mass, but roughly equal mass. Here in this case, barium and krypton are the daughter or the fission product. And in this case, there are 3 neutron release and there are also energy release. Uranium 235 usually absorb a thermal neutron, not a fast one. Fast one, you will just go inside and then no reaction will take place. Thermal means a slow one. And then it split into 2 nuclei. Now you can show it in your diagram there. Binding energy per nucleon against the nuclear number. And we can see there's an increase in binding energy per nucleon for the product. Further is uranium at the other end there. We are required to identify. We are required even to roughly estimate the position, right, from what is given. Barium 141, and then know that at the topmost there is 60, the most stable, and then krypton 92. Radioactive disintegration. Okay. This occurs when the original nucleus, this is the original nucleus, loses, right? This can be alpha, it can be beta, and if it is still in the excited state, it can still be gamma. When the alpha or beta is emitted, the product nucleus is lighter, this one, lighter than the parent. Okay, so if you look at binding energy of this one will increase. Binding energy per nucleon will increase compared to this one. Right? Example of radioactive decay will be your radium forming radon and helium gas. Or we can look at uranium 238, which is at the which is at the very end there. Uranium 238, when decay by alpha decay, give you thorium. Thorium is slightly away from it. But the binding energy per nucleon increases. Alpha is here. Okay, if we look at mass, this is greater mass than these two together. If we look at binding energy per nucleon, this one have a greater binding energy per nucleon than this one. Right? So radioactivity and binding energy. Basically, radioactivity is a spontaneous reaction. That means it just happened. You don't need any help. Just depend on the environment. The nucleus just decay. So radioactive disintegration is spontaneous, and fission can be too. Right? Sometimes fission take a long time, but you want to accelerate, then it give it a thermal neutron. If not, it will take a long time, millions of years. Right? We look into radioactivity. Next topic. In radioactive decay, the Q value, right, the energy release, is shared unequally between the emitted particle, alpha particle, and the required nucleus. This is the daughter. The daughter is the required nucleus. This is the alpha. Alpha particle takes away approximately 98% of the Q value as kinetic energy. Okay, you can try the worksheet. Question 6, which we are not going to try that. We'll give you roughly how to calculate, how to show that it's about quite high. And kinetic energy of alpha particle. You have to consider conservation of momentum. Example of this type of decay would be radium 224 and radium 226. So both fission and reactive disintegration lead to increase of binding energy per nucleon, and hence to release of energy as kinetic energy of product. If gamma ray, then gamma ray will be as one of the product. Does neutron have a binding energy? And neutron doesn't have. It's an individual particle. If it's hydrogen, deuterium will have a proton and a neutron, and then it has binding energy. Right? Neutron by itself doesn't. It has no nucleus. Nuclear fission and chain reaction. What does it mean? Okay, we see that in the fission of uranium previously, 2 neutrons are released. Right? 3 neutrons are released in addition to 2 daughter atoms. That's the reaction. Then there's the 2 daughter, and there's the 3 neutron. So this released neutron must go somewhere. So if there's uranium 235 around, then they will collide, and they will cause a reaction, and they will produce other neutron, right? Because self-sustaining, because it will keep on going. And this process is called chain reaction. Okay, here the same diagram, except we didn't show the daughter, that's all. Right? But we show only 2 neutrons. So the thing to remember is in each of these reactions, energy is released. And if the energy release is too high, then the gas will expand and there will be nuclear explosion. So in a nuclear energy reactor, we control the reaction. to harvest the heat to generate the electrical energy. Right? So chain reaction is a series of nuclear transformation change or fission initiated by a single nuclear fission. Is that like this one? That's your thermoneutron. There's a thermoneutron. It collides with a nucleus, uranium-235, and then it emits 2 neutrons. It can be 2, it can be 3, right? But you must have at least 1 to interact with another uranium. And then it produces 2 more, and then they carry on. Process carry on. Okay, let's look at nuclear fusion. Nuclear fusion reaction in which 2 or more elements fuse. Usually these 2 elements are lighter, not heavier one, lighter one. Fuse together to form one larger element, releasing energy in the process. A good example as shown in the diagram is the fusion of 2 heavy isotopes of hydrogen. This example will be deuterium. This is your deuterium. This is your tritium. And the product is helium. Okay. Where the product nucleus has a mass number smaller than 60. Right? 60 is the top there, the highest point there, iron. The binding energy per nucleon is increased by fusion process. Okay, just now we look at nitrogen. Nitrogen is about here, from oxygen. You can see that the binding energy release is going to be small. Right? So it's of no use to waste money to generate oxygen out of nitrogen because we have to put in energy first before it produce energy. That's why scientists won't bother about nuclear reaction in this area. Right? Only this part there we call fusion, and this part there we call fission. For much use because of the greater energy that's released. Now we can see the diagram there. Deuterium is there, binding energy per nucleon, and tritium is there. And you can see quite a fair bit of energy is released. We'll calculate that in a while. Right? We look at tritium, deuterium. Right? We force them to collide. Remember, we force them to collide. Then the nuclear reaction produce. Right? Fusion reaction release tremendous amount of energy and are commonly referred to as thermonuclear because heat is involved. Right? So we can think this type of reaction take place in the sun and in the stars also. So you can think of the sun as a large fireball. Yeah? Or the sun and the stars are actually fusion reactors. Right? Stars are primarily gigantic ball of hydrogen gas. And basically, remember, hydrogen gas is pulling each other together, and they are colliding. gravitational forces pulling them together. And then they collide, they fuse to form hydrogen, heavier element inside the star, releasing energy that we see as light and heat. Binding energy of the product is greater than the initial nuclide. Energy provided by fission and fusion per unit mass of reactants are much the same. Right? And of course, next question we ask is, then why are we interested in fusion? Right? We understand about fusion reactor, the nuclei of atom in fusion are positively charged. The first thing to remember, what is the problem with fusion? Both nucleus are positively charged. The deuterium and the tritium nucleus are positively charged. And for fusion to take place, the nuclei must be at least overcome the repulsive force. We call it Coulombic repulsion when approaching each other. They must overcome that before they can interact. And we have studied under Coulomb's law, the repulsive force is inversely proportional to the separation square. Means the larger the separation, the smaller is the force. Or the smaller the distance, larger is the force. If the separation is smaller, that will be larger. So this may happen if they collide at, so the only way to force a nucleus to collide is we use a high temperature. Then the two ions, right, deuterium and tritium, will be moving at high speed. Then they can overcome the repulsive force. Right? So the kinetic energy needed is of the order of 0.1 mega electron volt. In terms of temperature, is 10 to the power 8, which is very high. So at this high temperature, the gaseous atom doesn't exist as an atom anymore. It exists as what we call plasma. That means it exists as positive and negative charge, or we call it mobile ions. Normal atom anymore. Right? Positive nucleus and electron. So we can see that if we can cause fusion to occur, the large energy released in fusion provide a potential for controlling. Then we can control fusion to provide us energy in the production of electricity. Right? Covers it. Right? So the technical difficulty, you can see both of them are positively charged. At short distance, the attractive force, nuclear force, like that distance that we show. Right? The nuclear force is negligible. The repulsive force is large. So the idea is if we can send it so that it enter the nucleus of the other positive charge, then the nuclear force will take over. The nuclear force is attractive force. Whereas a positive nucleus, both positive nucleus will not interact because there's repulsive force. So that's why we have to push them close enough. What's the advantage of fusion? An abundance of fuel. Deuterium that we use in the reaction is found in the water in huge amount. You don't have to go and dig to it and go and find it. Water is everywhere. Waste product of reaction are generally not radioactive. Helium is inert gas, small enough to escape the atmosphere into space. Doesn't pose much danger to us. And then fear of nuclear reactor meltdown. Right? If it's a fission reactor, it melts down, you can see radioactive material will discharge into the water and to the atmosphere. Whereas in this case, there's no problem. Deuterium, tritium, and helium, they are not very active. Of course, there are problems. Okay, so you can read that yourself just for your general knowledge. We can use electric field and magnetic field to make sure that they move at high speed, collide, and then magnetic field to confine them. Okay, applying your knowledge. Right? The examiner like to see whether you know how to apply your knowledge. So why does nickel emit 3 gamma rays of different energy? Right? You do not thought you are supposed to be able to apply your knowledge. Right? When nickel emits gamma ray of different energy, it tells us that the nucleons in the nucleus, like electrons, exist at energy level. That means it's just like the emission spectrum of atom. The nucleons occupy energy level. Okay, so that's how we get our knowledge. Okay, applying our knowledge. Neutrons in the nucleus of atom, like electrons that circle the nucleus, exist in shell that correspond to energy states. The initial of the nucleus are less defined and less understood than those of the electron. These are just extra information for you, general knowledge. There's a state of lowest energy, what we call ground state, and discrete possible excited state for the nucleus, where the discrete energy states for the electron of the atom are measured in electron volt or kilo electron volt. The energy level of nucleus are in mega electron volt, very large. Okay, so we have completed this topic, mass defect and nuclear binding energy. Right? There's our energy release when the neutrons come together to form the nucleus. And then we calculate the mass defect as a total mass of nucleons minus the mass of nucleus. And then we calculate the binding energy, E delta M, right? Mass defect times the speed of light square. And then we divide binding energy by mass number to find the binding energy per nucleon. Large binding energy means large nuclear force. So the nucleus is more stable. And then we look at fission and fusion. Right? Energy release equals mass of reactant minus mass of product. And then the whole thing times the speed of light square. Or we work with binding energy, remember we work with binding energy of product and binding energy of reactant. So if we get positive value, then the reaction can take place. Negative value means energy has to be provided for the reaction to take place. Worksheet. Okay, page 358. We have the worksheet there. Now I can go to Facebook and download. Okay, try this yourself. Right? Here we are looking at calculating the energy that a body that's moving and hitting a body, there is a increase in mass. Right? Then let's look at 1 kilogram. What's the energy equivalent of 1 kilogram? Well, we just use Einstein's formula just to get you to memorize the formula by playing with the formula and calculating. We got that. So there's a lot of energy if we can harvest that. And 60 watt heater heats insulated metal electrically for 10 minutes. Calculate the change in mass of the block. Okay, that's what we say. We heat an insulated metal, the mass should increase. So let's calculate the increase in mass. ET, that's energy, power times your time, mass times your speed square. Put in your value, 60 watt, time is 10, 10 minutes, times 60 to change it to second. Mass M, that's what we are going to calculate the change in mass. You can put delta M if you want to, and as the speed of light is square M. Then we find that this mass is very small. The electronic balance cannot even measure this tiny change in mass. That's why we won't bother to correct it. When we hit it, don't bother to correct the slight increase in mass. Okay, this one you can try yourself. Let's try another example. Two deuterium nuclei fuse together to form helium-3 nucleus with a release of neutron. The reaction is represented by, it's given you, and then you are given energy, binding energy per nucleon. Remember, per nucleon. How much energy is released in the reaction? Okay, so we have to start with this one first, binding energy. So energy release is your total binding energy of product minus the total binding energy of reactant. So product, helium, that's one, helium. There are 3 of them. Remember this per nucleon, so times 3 nucleon. Get that? And then there are 2 of them here. Right? So for one of them, is this one, 1.09. Okay, and there are 2 nucleon there, times 2. And because 2 of them there, we times another 2 again. Then we calculate our value. Okay, C. Let's look at number 5, page 359. When uranium-235 nuclei are fissioned by slow-moving neutron, 2 possible reaction 1, reaction 2. It doesn't mean that there's only one reaction. Sometimes this reaction, sometimes this reaction, we don't know why. For reaction 2, identify the particle C, right, and state the number X of such a particle produced in the reaction. Okay, we start with looking at this one, number of nucleon. Total number of nucleon, right, initially is 235 plus 1. Finally is 139 plus 95, and there are 2 of them here. 235. Sorry, we are looking at reaction 2. This 235 plus 1 here, and 116 times 2. 116 times 2, and then we just call this one X. X number of nucleon, 4. And the conservation of charge. Okay. Conservation, this is 92 plus 0. This is 46 times a 2 there. Right? 2 daughter. And then we let that one be Z. Z. Charge, the charge in C be Z. And our calculation is 0. So the emitted particle is neutral. There's no other. The only non-neutral is neutron. So there are 4 neutrons. Okay. Binding energy per neutron E for number of nuclei is given in table below. State what is meant by this one. They will ask you to define. You have to memorize. Binding energy per nucleon is the total energy needed to completely separate all the nucleons in the nucleus divided by the number of nucleons in the nucleus. Okay, remember these are all binding energy per nucleon. Show that the energy released in reaction 1, that's a reaction 1, just to relate that, is 210. Okay. Binding energy release, binding energy of product minus binding energy of reactant, product 139 times that one, right? 839. That one is 95. SR 8.74, 8.74 there. And then for the reactant is 235. Uranium, and that one 760. Get 211 mega electron volt. The energy released in reaction 2 is 163 mega electron volt. Suggest a reason which of the two reactions are more likely to occur. The one that releases the most binding energy, it wants to be more stable, so you want to get rid as much energy as possible, then it becomes stable. So reaction 1 is more likely to occur as more energy is released in the reaction. Thus, the daughter's nuclei are more stable. That is November 97 paper. This question. Okay, now it might be flexible. Sometimes they give you atomic mass unit. Sometimes they give you energy. Now we work with kilogram. Suppose a stationary uranium decays spontaneously to thorium-234 nucleus emitting alpha particle. Write down the nuclear reaction. Right? That one you should be able to do. That's your AS work. Okay, that thorium has a mass M. No, I think I will calculate a bit, and the rest I'll let you do yourself. Okay, same thing. Suggest a reason which nucleus, uranium or thorium, has a greater binding energy. So it's usually thorium. Thorium, acid is more stable. So energy is released when uranium decays to thorium. Okay, so I will calculate with you a bit more. So you should be able to show that's uranium, that's your thorium, that's your alpha particle. Okay, I think I will let you calculate yourself this one, since calculation is more involved. Usually they don't come out. Okay, let's go to question 7. Consider the following reaction. This one is measured in kilogram. Determine the mass defect. You should be able to do that. Right? Mass defect, mass of reactant minus mass of product. So mass of reactant is this one. Deuterium, 2 of them. This one. This value times 2. And then minus the mass of that one. That one. I take 10 to the power minus 27 out. And then this is for your neutron. Get this value. Right? Don't round off. Keep the number of decimal place. Then use your E equals mc squared. That's your basic calculation. That's your mass. That's about 27. Speed of light. For that, is the reaction endothermic or exothermic? You can see energy is released positive. Exothermic. Okay, let's look at this one. A collision takes place between an alpha particle traveling at the speed is given you. That's the speed alpha. And a stationary, this is stationary nitrogen. It results in the following reaction. They're giving you the reaction, they're given the mass, atomic mass unit. The particle move in a straight line as shown in figure 2. The speed of the proton, after the collision, that's the speed of oxygen, we don't know. State the number and type of particles that form an alpha particle. That's AS work, you should be able to do. 2 proton, 2 neutron. Calculate the small change in mass in kilogram, which take place in a reaction. Okay, so we are working with mass, remember? So we have to start with mass of reactant minus mass of product. Okay, that is your reactant. That is your product. Subtract. Got that? Minus sign. as we expect. We have calculated earlier in the lecture. Calculate out, we are not worried about negative. Negative tell us that it's endothermic. That means the reaction cannot take place unless we give it energy. Calculate out. This one is just to calculate only. So we don't want the negative value. And then the energy release must release as kinetic energy. Minimum kinetic energy, delta M mc squared. That's your mass, delta M. That's your speed of light, square M. That's what we get. Okay, and they tell you, use the principle of conservation of momentum, find the speed. That's your reaction. Right? So taking to the right as positive, remember momentum is a vector quantity, so you have to choose the direction to the right as positive, to the left as negative. The total initial momentum equals the total final momentum. So we look at the, don't need to change the kilogram because you are trying to find the speed. So if all of them are same atomic mass unit, it's okay. Right? The speed will follow the unit that we use. So that's the mass of helium and the speed of helium. Nitrogen is no speed, so you don't know border. And momentum, oxygen. Oxygen you are given the mass and V. Hydrogen, proton. Okay. Mass is given and the speed. Then we get positive, so it must be to the right. Okay, let's try one more. Uranium nuclei, when bombarded by neutron, may undergo nuclear reaction. Okay, this is your AS work. You should be able to write the nuclear reaction and then determine what is the unknown to neutron. And then it's straightforward. It's a nuclear fission or fission reaction. Okay, we are just repeating the common thing that come out in binding energy. Binding energy for a neutron of uranium is 7.5. Barium, that estimate the energy change in the nuclear reaction. Right? Remember, binding energy per nucleon. Okay. So you are told barium and krypton roughly have the same one. Right? But 144 plus 90. Remember this per nucleon and that is the product. Binding energy per product. Binding energy of the reactant 235 and 10.5, we get 227 mega electron volt. Right? So whether suggest two forms of energy into which the energy is transformed during the reaction of this type. Right? So it's kinetic energy of the fragment, it's a barium and a krypton, or can also be gamma rays. In nuclear reaction, it's always gamma rays that's emitted. Okay, so you can try yourself the partial paper. All the best to you. You end the lecture now.